Have you ever wondered how services you use every day, such as Google, are always online and never down? My name's Adrian, I'm the Senior Cloud Engineer at ZSecurity, and today I'm going to teach you some basic high availability concepts and show you how you can deploy your own highly available application using Linode's infrastructure with automated failover and multiple redundancies. If you've never done this before, don't worry. We're going to be creating the servers from scratch and installing all of the software ourselves. I will walk you through every command and every configuration directive. For those of you that haven't used Linode before, Linode offers a reliable and affordable way to deploy virtual servers that we can access online. If you use the link in the description to register, you will also receive $100 free credit that you can use to try out your own applications. Let's cover some background and terminology first. High availability, or HA, characterizes systems that are dependable enough to operate uninterrupted for long periods of time. Uptime is the most common measure of dependability. You've probably heard of claims like 99.99% uptime. This would mean that in a given year, a system was only down for about 53 minutes, which is an impressive feat. High availability can be boiled down to three main principles. Number one is the elimination of single points of failure. A single point of failure is a component in our system that if it were to fail, it would bring down the whole system. You can think of it as an Achilles heel. To address this, we generally add redundant components. Redundancy, as shown here in the diagram, is the duplication of important components in our systems to make it more reliable. For example, commercial aircraft implement multiple flight and engine computers. Sometimes they even use different software versions between them. If your entire service depends on one server, one database, one switch, and so on, the effects of a sudden crash can be disastrous for your users. Number two is reliable crossover. At some point, and for a variety of reasons, components we deploy, whether we consider hardware or software, will fail. If a component fails, redundant replacements should take over. To minimize interruption, this process needs to be fully automatic. Ideally, users of the system should be unaware that this is happening. Since switching will always take some time, whether it's minutes or milliseconds, we may not always achieve 100% availability. Our goal, however, is to get as close to this as possible. And number three is the detection of failures as they occur. If we've implemented redundancy and have automated failover, this condition should already be satisfied. Failover is just a fancy term for switching to a redundant or standby component in the event of a failure. The system design we will follow later in this video will employ a master server coupled with one or more standby servers. Heartbeat network packets, consisting of status messages, are broadcast and evaluated to deploy measures if a failure has occurred. So why is high availability important? Put simply, customers expect it. A single component's failure could knock a site offline. In order to ensure user satisfaction and meet service agreements, solutions must be implemented to avoid such failures. Availability can, of course, impact industries differently. For example, e-commerce, social platforms, and online gaming services are completely dependent on their sites working properly. Other industries, like B2B, SaaS companies, risk upsetting their end users if they cannot access the information they need to complete their jobs. At the same time, availability is non-negotiable for industries that meet urgent needs, like medical or emergency services. Before the mainstream adoption of cloud computing services, high availability would have been implemented through on-premise setups. Not only would the cost be astronomical in terms of hardware and IT teams, but generally, only the most critical business services could be made highly available. Scaling these systems would be a major challenge too, since we need to anticipate load, purchase additional hardware, and run numerous tests to validate our configuration. Thankfully, this no longer applies. The examples I will show in this video will be deployed on Linode's cloud infrastructure. With Linode's cost per usage model, we can scale the application as user interaction increases. We simply add or remove servers as needed in order to balance load, cost, or ensure redundancy. We can therefore achieve basic high availability for a fraction of the cost of on-premise setups. The failover model that we will implement is IP failover. The first step to implementing IP failover is allowing multiple Linode compute instances to share a single IP address. One server will act as the master, or primary, and in the event of a failure, one of the standby servers can be assigned its public IP and continue serving requests from users. We will install software which monitors and reassigns IPs on each master and standby server. We will satisfy the principles of redundancy, reliable crossover, and automatic failure detection with a software package called keepalived. Keepalived implements a virtual routing protocol that is used to monitor servers and automatically execute IP failover. As the name suggests, keepalived is a daemon. It is installed as a service and runs in the background, periodically broadcasting status messages. Should the master compute instance become unavailable, the IP address will seamlessly fail over to a standby compute instance. If or when the master instance is back online, the IP address will fall back to that instance. This process is invisible to users interacting with your system. To visualize this, consider the following diagrams. During normal operation, the user requests data from site.com, which is located at the public IP address 9.9.9.9. Fulfilling this request is the master server. keepalived is running on both servers, monitoring their status. Now, suppose something happens to the master server, and it is no longer able to transmit heartbeats. Once a configured timeout passes, keepalived will reroute traffic from the master to the standby, ensuring continued operation of our service. Let's follow a simple workflow. We're going to create two basic LAMP servers running Debian. We need to configure IP sharing between them. Now, IP sharing is supported in most Linode data centers, but not all of them. I've chosen the Dallas, Texas data center for convenience. I'm using LAMP here purely for convenience as well. An NGINX package, for example, should work too. We will then install and configure keepalived on both servers and test failover in a few scenarios. Let's jump in. This is the main Linode management panel. After logging into your account, you will see this screen. Let's start the process by clicking Create Linode. It's very easy and should only take us a few minutes to have a fully working web server. Let's go to the marketplace, where we can find a variety of pre-configured applications to choose from. Let's find LAMP. Next, we need to fill in a database root password. Make sure you use a secure password here, as this is the password that applications use to connect to your database. I've already got one in my clipboard that I will now paste in. An email address is now required for the auto-generated SSL certificate. Next, we will select Debian 11 as the operating system image. Debian is a very stable and widely used Linux distribution. The setup would be identical in Ubuntu and other Debian-based Linux distros. Select Dallas, Texas, as this is one of the data centers with IP sharing enabled. Next, we will need to make a choice for which plan we are going to use. The smallest instance available offers 1 GB of memory and a shared CPU for $5 a month. This will be more than sufficient for our test web server. However, you will need to consider the resource consumption of any production web applications you deploy on your server. Let's set a meaningful label, such as LAMP master. This will help us keep track of the instances. Finally, we need to set the server root password. This password is very important, as it is also used to authenticate to the server over SSH. A weak password will allow malicious users to connect to the instance and execute commands. For increased security, we could create an SSH key instead. However, to save a bit of time, we'll use password login instead. And that's it for the configuration. We should now be ready to create the Linode. Okay, as you can see, it is now provisioning. It will take a few minutes for it to come online. With the instance now running, let's go to its public IP and test that Apache is able to fulfill our requests. Great! We can see the index page that Apache ships with. Now, let's go back and adjust the network configuration. Click on Network. We will need to add a private IP in order to allow the master to communicate with the standby instance. To do this, click on Add IP address. Select Private and click Allocate. That's it. If we refer back to the diagram, the master instance is created, has a private IP assigned to it, and it responds to requests on its public IP. The next step is to install keepalived on its operating system. To install keepalived, we will open a Lish console. The Lish console lets us run commands on the operating system. First, we log in as root with the password that we entered when creating the instance. Since everything is up to date, all we need is one command: apt install keepalived-y. This tells apt, which is the Debian package manager, to install a package named keepalived. -y skips the confirmation prompt. And that's it, keepalived is now installed. Let's now minimize this console and go ahead and create the standby instance. We'll click on Create, Linode. Let's go back to the marketplace and select LAMP. Fill in the database root password, the email address. Select Debian 11 again. And we will need to select the same region in order to enable IP sharing between the instances. We'll use the same configuration. Adjust the label so that we can identify this is the standby instance. Set the root password and hit create. So the standby instance is now provisioning. As with the master, it will take a couple of minutes for it to come up. With the standby instance now online, let's go ahead and adjust its network configuration. First, let's add a private IP address like we did with the master. Now, let's enable IP sharing. IP sharing will allow keepalived to assign the master's public IP to the standby in the event of failure. To enable it, click on IP sharing and select the master's public IP address. And click Save. That's it. IP sharing is now enabled. Next, we will need to install keepalived on the standby instance. To do so, we will need to open a Lish console. Like we did with the master, we will log in as root and run the same command that we did last time: apt install keepalived-y. Okay, keepalived is now installed on the standby as well. So the master is created and has a public IP, a private IP, and keepalived installed. The standby is created and has a private IP, permission to use the master's public IP, and keepalived installed. However, there is no communication between them yet. Keepalived needs to be configured first. The configuration file for a basic setup is quite simple. I've used the minimum number of directives required, and will walk you through all of them. We need to create this file for the master server and any additional standby servers we create. For the purposes of this video, we will only need to do this twice. We start by defining a virtual instance and naming it. I've named it vi_1. The name itself is not very important as long as it is kept the same for both servers. Meaningful names help keep the file organized. I've set the virtual router ID to 51. This identifier allows us to create multiple keepalived groups on the same network. We might have multiple groups if we're duplicating different resource types that we would like to keep separate. Dedicated database servers, for example. The ID must be set to the same value between the master and standby servers we'll be configuring. The priority can be set to an integer between 0 and 255. This parameter is used to specify the order in which our servers take over in the event of a failure. For this reason, we will set the priority of our intended master higher than that of the standbys. The advert_int setting of 1 tells keepalived to broadcast its heartbeats once every second. Heartbeats are the messages sent by the keepalived software running on master and standby servers. We're trying to strike a balance between sufficiently fast failovers and not flooding the network with unnecessary communication. Lower values will generate more noise but result in quicker failover response since the heartbeat content, or lack thereof, triggers failover. In the authentication block, we're requesting keepalived to use authentication headers as opposed to plain authentication. The addition of these headers allows keepalived to authenticate the sender and discover any changes in data during transmission. Although very unlikely, this setting will mitigate scenarios where an attacker is trying to inject malicious heartbeats into the network. The unicast source IP is set to the private IP of the server on which this configuration file resides. The unicast peer block is filled with the private IPs of other servers on the network that are part of the failover group. In this case, the master's peer is the standby, and vice versa. Finally, the virtual IP address is set to the shared public IP that clients use to connect to our service. Here, we can see the configuration file for the master and standby side by side with the differences highlighted. Mainly, the priority of the standby is one lower than the master, and the corresponding private IPs have been filled in. With the two consoles side by side, master on the left, standby on the right, let's begin configuring keepalived on the master. The configuration file does not exist yet. We need to create it. I will be using a text editor called VI. When running the VI command, the file will be created automatically. So we type in VI and the location /etc/keepalived/keepalived.conf. Okay, since we've already defined the configuration file earlier, let's paste it in. Press Insert, Ctrl-Shift-V, and then let's save with escape, :X, and exclamation mark. This tells VI to exit and save the file. With the configuration file now in place, we need to enable keepalived service so that it can run in the background. The command systemctl enable keepalived will do so. Okay, next we will need to start the service with systemctl start keepalived. Now that keepalived is running, we should check the logs and make sure that everything's going okay. With tail-f/var/log/messages, we are able to read the message log from keepalived and watch as any new entries are stored. Keepalived is now running and sending heartbeats to the standby instance's IP. We need to configure and start keepalived on the standby as well in order to enable failover. The steps are almost identical. The only difference is that we're going to paste the standby config. We type VI followed by the location, press Insert, paste, and then save with : exclamation mark. We then enable keepalived service, start keepalived, and monitor its logs. Okay, we can see keepalived started successfully, and more importantly, it is entering backup state on the standby instance because the standby instance has a lower priority than the master instance. So everything is working as it should. This is indicated here on this line, where we can see we received an advert from this IP with a higher priority than ours, which is 50. Okay, so let's see what would happen in a simulated scenario wherein the master is turned off. Let's minimize this console, start pinging the master's IP, and now off screen, I'll power off that Linode. This will take a few seconds, of course. Okay, so what we can see is that the standby took over the master state. The pings were completely uninterrupted, so clients cannot see what happened. And more importantly, let's check if we can still access the Apache built-in page on that IP address. And we can. Let's demonstrate this in more of a visual sense. What I have here is a Chrome script that's constantly refreshing the master's public IP. I've also edited the built-in Apache pages to differentiate between the master and the standby. As we can see here, I am the master. Now let's see what happens if we go and shut down the master. Click power off, and let's go back. So the master is shutting down. And now we can see the standby page. The change did take a few seconds to show. However, if we were serving identical pages, users would never notice. Let's power the master back on and watch it take over from the standby. Okay, the standby has now entered backup state. And now we can see the master page. The previous configuration triggers failover in scenarios where the master or standby fails to send out heartbeats. For example, if the server itself crashes, keepalived crashes, and/or network communication between the servers is disrupted. Oftentimes, this is not enough. In our own experience, it's much more likely that something running within the operating system causes downtime. An out of memory triggered by a crashing database, for example. We can configure keepalived to monitor the state of processes on the operating system. To do so, we simply create vrrp_track_process directives for each process name we wish to track. We invoke the directive names in the track_process block of the vi_1 instance. I've chosen the two most important processes in a LAMP setup, the Apache web server and the database. If either of these processes crashes on the master server, failover is triggered. Let's make the configuration changes. With the master and standby consoles side by side, we begin with the master. We open the configuration file in VI. Then, we press Insert and paste the directives at the top of the file. Then, we invoke them after the virtual IP address block. We then press Escape, :X, and exclamation mark to save. Next, we will need to restart keepalived. To do so, run systemctl restart keepalived. Let's do the same for the standby, VI and the location. Go to the top of the file, paste the directives, and then invoke them. Press Escape, :X, exclamation mark, and then restart keepalived. Let's run another test. The browser is loading the master's public IP address every half second. On the master, let's stop the Apache service, which we're tracking in keepalived, with the command systemctl stop apache2, and watch what happens. The standby took over the master state, and after a very brief interruption, it's now displaying its own Apache page. Now let's bring it back. The standby node now went into its backup state, and the master is now serving its page. By now, you should understand how to set up basic high availability using keepalived. As mentioned before, the main benefits to making our services highly available are a reduction in user disruption, fulfillment of any service agreements we might have in place, and uninterrupted provision of critical services. This increases user satisfaction and avoids lost revenue. You can learn more about keepalived and its documentation at keepalived.readthedocs.io. With Linode, we were able to demonstrate this with 2 instances that would cost us a combined $10 a month. And remember, if you sign up with the link in the description, you will also receive $100 credit that you can use yourself. I hope you were able to follow the explanations and enjoyed watching the video. If you did, please let me know in the comments.